now we find the slope of the secant of where x is 1.5, so the point for that is 1.5, and we said that this was 3.75. So this is going to be 3.75 minus 3 over 1.7 or 1.5 minus 1. This equals to 0.75 over 0.5, which is 1.5. So that would be our slope at x equals 1.5. And now the next one is the slope that we need to find for the next point on the curve, which is 0.5 for x, and we found 1.75 for y. And so we plug that into the slope formula, y2 minus y1 over x2 minus x1. So y2 is 1.75 minus 3 over 0.5 minus 1. And this is a negative 1.25 over negative 0.5. And this gives us 2.5. So we pick 3 different points away from the 1.3, and we get these different slopes. Now, what I would like to have seen them do in this particular problem is take 2 on one side of the point and 2 on the other side, and then kind of average them out and see what happens here. But if we just look at these right here, we can see that the average of those 3 slopes is in the neighborhood of a little bit more than 1.5. 4, 5, 5 divided by 3 is 1.67. So it's about 1.67. So this is one way that you can estimate what a slope is, but you're better off picking points that are somewhat close and on opposite sides to get that. Okay? But that's what they're looking for you to do. So you're going to do problem 8 that is very similar to problem 7. Same process. These lines again, I'll refresh your memory. These are called secants from one point to another point of the curve. A chord of a circle is when a line is drawn through a circle, it intersects the circle 2 points. That part where it hits the one point in the circle to the other point of the circle, that's called a secant as well as a chord. They're the same thing. Okay? So now let's take a look at problem number 9. Problem number 9 deals with areas. So what they've done here is they've taken a curve and they're estimating what the area of the curve is, or the area under the curve from where the 1 is for the x to the x equals 5, the x-axis, and then that little curve right there. So that lavender colored area is what they're actually looking for, but we're going to use approximations with squares, or rectangles rather, that begin at the point of 5 and stop to the point of right around 1. And then the 2 graphs here, what they show here, is that they go by 1s across there, and then they cut it down even smaller areas where we have 0.5s. Now we know that the answer is going to actually be above what the actual curve is because we've got a lot of blue areas above the curve. The question is, which one is the better of the 2? And can we kind of guess about what the area is going to be based upon the change that we see there? So let's take a look. So what we're going to do is we're going to find the area of each rectangle. So we're going to call this rectangle 1, 2, 3, 4. And we estimate the height of each one and multiply by the width, which is 1, because the area of a rectangle is length times width. We get 5 times 1. I estimated the next one to be about 2.6. It looks like a little bit above 2.5. You say 2.5, that's fine. You know, these are all estimations. 2.6. Next one looks like about 1 3/4, so I put 1.75. And the next one looks like about 1 1/4, so I put 1.25. I added these 4 up and I get 10.6. Okay? Do the same thing with the rectangles that are half the width of the other one. It turns out there's 8 of those things. And again, you have to estimate. Now, this is where we lose the accuracy because we don't really have a good scale here. So we've got to eyeball this thing. And some people's eyeballs are better than mine, mostly. But we'll eyeball this and see what we get here. And I found 5, 3.2, 2.5, 2, 1.8, 1.6, 1.4, 1.2 for the heights of those 8 rectangles. And then I multiply by 0.5 to get the area, and I add all 8 of those up, and I get 9.25. So what's that telling us? Well, here are a couple of things here. First of all, when we chop it into smaller bits, we get a value that's less than the big bits. It's a difference of about, let's say about between 10 and 15%, which is significant. Neither one is accurate, but I would say that this is the more accurate because if you take a look at the diagram, there's less blue area in those rectangles on the skinny rectangles as opposed to the fat rectangles. And so if I would take a look at that and I'd say, okay, the fact that I went by half, the difference is, like I said, about 14%. If I go by half again, it's going to be a little better. I keep going half again, it's going to be a little better. I keep going until it gets to a point where there is no difference between the two. We call that an infinitesimal difference. And when we get to that point, we can figure out exactly what it's going to be. Because infinitesimal differences mean you are counting 2 consecutive points that have virtually no distance apart. So we are going to be developing mathematical formulas that will give us those values. That's what the calculus is going to be. So you're going to be doing problem 10, very similar to what we did right here. Problem number 8, similar to what we did there, and that'll be your first assignment. And have fun with that. Again, if you get stuck, talk to me. We'll get you through it.